Sorry, so I have to switch to English, and this is recorded. So it's a great pleasure to have today with us Carla Gobel from the Pontifical Catholic University of Rio de Janeiro. Carla did her studies, undergraduate studies in chemistry at the same university, but later she switched to physics, and she did her PhD in CBPF, also spending a sandwich period at Fermilab, studying particle physics, high energy physics. And she worked at the University of the Republic in Montevideo, Uruguay, from 1998 to 2003. And since 2003, she's a professor at PUC Rio. She works with, her field is high energy physics. And in this field, her area is flavor physics. So this is physics that studies quarks and leptons. And within this field, there are even subfields, quite large subfields like charm physics and bottom physics. So this is a field of specialization of Carla. And today she will talk about this and about the experiment, the LHCb experiment at CERN. So please, Carla, the floor is yours.
Good morning. So it's a real pleasure to be here. It's my first time at an international institute, not my first time at Natal. I'll be here again next year. I hope you all be there for the ICEP that we are organizing. So it's going to be a challenge, but it will be great. So I want to, well, Farinaldo is not here, but I want to thank him for the invitation. And one thing that he said is that everybody here knows particle physics and I have to explain nothing, which is not quite true because I know now that there are people here from outside the area, but this is, I mean, really feel free to ask anything because as Dimitri said, I'm going to talk about flavor physics, which is not exactly what you do here too. So it's going to be, this is an opportunity, I think, for you to see other aspects of high energy physics. So the title of my talk is this, the eclectic physics of the LHC experiment, because although LHCb was born, the original idea was to do CP violation and search for rare decays in B physics. It really expanded a lot since its beginning, and it really covers a wide field in particle physics. I don't have the time to talk about everything, and it's going to be very boring too. So I'm going to highlight the things that I find more fascinating, and let's start. So the idea is that, you know, the standard model. So the standard model is this quantum field theory that has this challenge to describe all the particles and all the fields and the interaction among them, and it's a very successful theory. I'm not going to go into the details of it, but we know that we have 6 quarks, 6 leptons, and the forces and the Higgs fields that gives mass for everybody. But of course, it's a little bit more complicated than that. We know that, for instance, these forces, the gluons itself have like 8 gluons, and then you have the leptons, but then the anti-leptons and the quarks that further come with 3 different colors each, and the anti-quarks. So this is a bit more complicated. So in fact, I need one more slide because to what I want to talk you about is the flavor sector of the standard model. So this is the Lagrangian, doesn't matter, but what I do want you to pay attention is that in the gauge sector we have the 3 parameters of the standard model. We have the 3 gauge couplings. So 3 parameters means that we have to measure them. They are not predicted by the standard model. So we have the 3 gauge couplings to the describing the 3 interactions. Then we have the Higgs sector that have 2 other parameters, the VEV and the Higgs mass. And then we have this rich flavor sector describing the leptons and the quarks coming each in 6 flavors and masses. So let me also point here that in fact what I'm putting here, I'm including the neutrino masses and lepton mixing matrix, which is not embedded in the standard model, but we know that are there. So in fact we have 20 parameters in the flavor sector. So the flavor sector is a rich sector of the standard model. We know that the standard model has a very successful history of success. I'm showing here very quickly all the particles when they were predicted and when they were observed. Some of them have a big lack of time, like the Higgs, and some have the inverted pattern, like the muon that was first observed and then predicted, let's say postdicted. But anyway, so we know that although this big history of success that somehow culminated with the observation of the Higgs boson at the LHC in 2012, we know that it has limitations. So there are many questions that still we don't have answers, like the matter-antimatter asymmetry. We're going to get into that as one of the things that we are going to discuss today, that although the standard model has a mechanism for that, it's like many other of magnitudes lower than we should have to explain the matter-antimatter asymmetry. The hierarchy of masses from neutrino masses to the top, there are many other of magnitudes. As I said, many free parameters, and also the cosmological observations that we have that are dark matter and also dark energy, that have this link of particle physics and cosmology that we don't really have no idea what's going on there. So the idea is to try to answer or attack these questions doing in 2 main frontiers. One is the energy frontier, which is we go higher on the energy of the experiments, but we are very limited on that. And then the precision frontiers, that is measuring all the parameters and constraining them with more and more precision, because always the high energy particles leave prints at lower energies. So this is the focus. So LHCb works on this frontier, but also the next high Lumi, it's going to be the next generation of the LHC is going to be high Lumi, not high energy. So we are going to work more and more on the precision frontier. So the flavor physics, so I'm going to talk about flavor physics in the quark sector, which is what I do. But we have many examples on how flavor physics gave hints of phenomena that were occurring at a much higher mass. So for instance, the W mass, that it's about 80 GeV, the beta decay that was observed for the first time at the beginning of the 20th century, it's a very short distance interaction, and we knew already, if we believe on propagators, that the propagator should have a very high mass. But other examples, like the prediction of charm because of the tiny rate of k short to mu mu, or CP violation in neutral kaons, that meant that we had to have 3 families of quarks, and also B0 bar oscillation that happens at 5 TeV gives infer the mass of the top quark, which is 170 GeV. So I think I can convince, but this plot also show you more or less, you're not going to see in details, but these are many observables in flavor physics, and how these observations are giving, excluding limits for the mass of new particles, that some of them go up to 1,000 eV, depending on the observable. Anyways, so flavor physics. So flavor physics deals with the fact that we have 3 generations. We have a repetition of quarks and leptons in 3 families. So there are 6 flavors for each. And the richness of the flavor physics is the alchemy. So the weak interaction is the charge weak interaction is the only interaction that can change the identity of the particles. So for instance, a D quark can, I can use this, right? The D quark can be transmuted to the U quark, and the electron can transmute to a neutrino, and so on. And this, in fact, is the reason why at the beginning of the universe, where we understand that all particles were generated, soon after, because of its getting expanded and cooler, we end up with a universe that is now dominated, the matter is dominated only by electrons and protons and neutrons, and the neutrinos that are there anyway. So how that happened? So I'll start with this topic, which is very important for what we are going to see today, which is the baryogenics, or why there is more matter than antimatter in our universe. So we believe that matter and antimatter were equally produced at the beginning of the universe, and we have enough energy, enough temperature that photons could create all kinds of pairs of particles and antiparticles, and they can annihilate again, and it's a process that was common. But since the universe began to freeze out, you have annihilations of protons and antiprotons, and then we didn't have enough energy to create them back. So in fact, we would end up with a universe that would be only radiation. But this is not what we see, right? What we see is highly, but before saying this, and we have proof of that because of the cosmic wave background, that we know that the universe is with a radiation that it's very very homogeneous at 2.7 Kelvin. Sorry. So what we observe today is that although there is this extra matter, but the level of matter that survived, that means not everything annihilated, there was this little matter that didn't find their pair to annihilate. So this number is around 10 to the minus 9, 10 to the minus 10 of, at the beginning of universe, having more baryons or leptons than anti-baryons or anti-leptons. This is known as the matter-antimatter asymmetry. And we know from the Sakharov conditions from 1967 that for that to happen, you have to fulfill these 3 conditions: some mechanism of baryon number violation, C and CP violation, and transitions out of thermal equilibrium. So C and CP are discrete symmetries. We know that CPT is required for Lorentz invariant. So any quantum field theory has to respect CPT. But we know already that CP is violated, which means T is also violated. And CP violation, when I speak about CP violation, it's the same as speaking about that matter and antimatter decays differently, depending on the process. So we know this since 1964, and there was the prediction of Kobayashi-Maskawa that that would mean that we have to have at least 3 families of quarks and leptons. We're going to going back to this, just a quick, let me put this, just a quick comment on how we observe CP violation. There are three main mechanisms. So CP violation means that particle and antiparticle, they behave different. One way is what we call a direct CP violation, which is we count the number of decays of a given particle, B+, and see how many events we observe. Count the same for the antiparticle, B-, and count. Correct for acceptances and whatever, and if this number is different, this is what we call direct CP violation. Indirect CP violation is interesting because if we would, let's say, talk to a different universe that we are not sure whether in this distant galaxy they are made of particles or antiparticles, we would say what I call particle is for B+ or B- that decay more in K pi pi. That is what I call particle. What is that you call particle? And if they call the other way, maybe they are antiparticle galaxy. We know that there aren't galaxies made of antimatter, but I mean, this gives an absolute distinguish between particles and antiparticles. Then there are CP violation in what we call mixing and in the interference between mixing and decay. We know that neutral particles like the D0 or the B0 or the BS, they can oscillate. Particle can become an antiparticle, and this goes in time, and they change one to another. I'll go into that. And there are some signs of CP violation that occur in this process. I said that was going to be quick. So CP violation in the quark sector. From now on, I'll be talking only about CP violation in the quark sector. We know that the CP violation also occur in the lepton sector since neutrinos oscillate, and is expected that the CP phase in the neutrino sector is very large, but this is everything I'm going to talk about it. So we know that from the Higgs mechanism, all quarks acquired mass, but then this already creates a new feature, which is the fact that the weak Lagrangian or the weak Hamiltonian does not commute with the free states. So the bases are different. So from going to the free states or the mass states to the weak base, you have to have a transformation, a change of bases. This change of bases means for three families that you have a 3x3 matrix that transform the mass states to the weak states. And this matrix is a 3x3, but it can be complex. So there would be in principle 18 parameters. It measures the probability of transition among the families. But since it can be, it has to be unitary if we believe that there are only 3 families. So being unitary, these 18 parameters reduced to just 4, one being a complex phase. And this complex phase means that the same matrix for anti-quarks can be different. So it means that processes for quarks and anti-quarks have different phases. So if we can access phases through interference, right? So we have to see what kind of processes we could be able to see these phases. The problem with the CKM matrix is that it is almost real and it's almost diagonal. So in fact, these transitions among families are small, and also the CP violation effect is small. So we have a small component of CP violation. We can put this matrix in terms of expansion of this parameter, which is the sine of the Capibel angle. Doesn't matter, but you see that it's almost diagonal, and the phase that leads all CP violation that we see in the standard model, in the quark sector. It's in this term and in this term. And this means two types of transitions. We can see CP violation directly in any decay of the B changing to U, where you can have the VUB, which is this one, or in what we call penguin processes, that the B goes to a top and then the top goes to a D and there is an emission here. So these are the main processes for which, for instance, if I interfere these two processes, I can be able to see CP violation. Also, this means that in other, this is why in B decays it should be high levels of CP violation, but we should expect tiny effects on charm decays, which is what I work on. Just another technicality that I'm just going to show you, because I want to show you a very beautiful plot, is that the unitary conditions of this matrix imposes constraints. That this means that there should be a triangle relating the sizes and the angles. The fact that this is a triangle means that there is a phase, otherwise it should fold in itself. And the idea is to measure these angles and these sides independently, to over-constrain and to see if the ansatz of a CKM that the standard model gives is the correct one. And as I said, I just want to show you this because in 1995, there were very few observables on CP violations and on the sizes of the CKM matrix. And for instance, you have oscillations of kaon, you have a very limited information on this. This is CP violation in the kaon sector. And these independent measurements, this is the over-constrained, where they meet each other, should give the apex of this triangle. And at that time, it could be in any place in this orange curve here. And what I'm going to show you is the evolution of that in 30 years. So in 2001, it was the observation of CP violation and the B decay. So this angle beta was measured, and this constrained to this region. Then there was further measurements, and then this is where LHCb entered the game, because we could measure gamma. So this here constrained this apex much more. But what is interesting is that many other measurements always come compatible. I mean, there is a single region where they all cross. And sorry. Oh, I have to go all over again. And this is where we are. You can barely see here. So all measurements together point to this. This is awesome. But anyway, let's move. So I'm going to talk about very bit about LHC, and then move to LHCb and the main results that we are having. So you should all know this by now, but for completeness. So the CERN is an international laboratory, so it's in fact a condominium, and institutes and countries can join. Any institute can propose an experiment to be based on CERN. Has to be proposed by any of the member states. But CERN itself cannot propose any experiment. This is interesting, I didn't know about that. So there are many member associates. To be a member state, it's have to be European. And then there are the associate members that Brazil has joined since 2024. There is no new plot like this. So LHC is, so there are many experiments at CERN. I'm going to talk about the main experiments that occur at the Large Hadron Collider. It's a 27 accelerator ring between Switzerland and France in the frontier. They are all more or less 100 meters below ground, and these are the 4 main experiments. These numbers are a bit not quite correct by now, but the order of magnitude is correct. Brazil is part of the 4 main experiments, and also in the Alpha, which is an antimatter production experiment. So I work here at LHCb. So let's go to, these are some numbers. I just want to point out these impressive numbers, which is, I don't know if you do know this or not, but in fact the protons goes in bunches. So they are more or less 2,400 bunches simultaneously in one way and in the another. And they are meant to collide in the 4 points where there are the 4 experiments. There is this 25 nanosecond spacing between each of the packages, and each of these bunches have about 100 billion protons that then are very collimated to collide. This is it from here, and let's move to the LHCb experiment. So the LHCb experiment is a bit different because it's the only forward detector. What does this mean? It's not a barrel like the other ones. It is meant to observe particles that are produced in the forward direction. So more or less, so this is the cavern, and this is the experiment. This is the collider point. And we see particles that goes in this direction. Of course, the particles goes in the other direction too, but we don't have a double experiment to the other side. The main ideas here is to study heavy flavor physics, decays, production and decays of B and C quarks, but as I said, not only. The original goals was to study CP violation, search for new physics by studying rare decays, and also hadron production and spectroscopy, including new state, among other things, in fact. So we work at the precision frontier. What we have as different is that we have excellent tracking capabilities that we can separate. I'm going to go back to this, what we call the interaction point and the decay point, because B and C quarks typically travel about 1 centimeter. So if I can separate what is the interaction, proton-proton collision, from the decay point where these particles decay, we can separate them from background, which is a capability that CMS and ATLAS cannot do. And also we have excellent particle identification. It's crucial for us separate what is a kaon, what is a pion, a proton, an electron, and muon. Otherwise, it's impossible to do what we are meant to do. So, as I was saying, a forward detector means this is a simulation, but when you produce proton-proton goes and you're having to create proton against proton is matter against matter. And if you have to create a bottom-anti-bottom pair, they are going to be created in the same direction. So either one way or the other. So we put a detector in one of the corners. While the other experiments, like CMS and ATLAS, see the frontal region. So we work at this region of pseudo-rapidity, which is frontal, while they go in the high angles. So Higgs, heavy particles are produced at high angles, and we go to these angles. Also, we work at a much higher, much lower luminosity, because we have to really reconstruct each trajectory. So it's very important that we don't have a mess. Hadron collisions are already a mess. So we set up the luminosity to have just one collision per each bunch crossing. This was the conditions in run 1 and 2, but now in the run 3 that is going on right now, we had an upgrade detector and we could go to about 5. And this is going to be even higher for the high Lumi. Anyway, so I'm not going to talk about all of these things that we have in LHCb, but just for you to know the types of physics that we do. We can do electroweak physics, we can do high PT and look for exotics like axions, or we have a recent measurement of the Z and the W mass, so there are things that we can do. And also we do heavy ions like Alice, and we also have a very special and unique program on fixed target physics. I'm not getting into that, but so for you to know, when you have proton and proton, this is one mode of collision, but we can also put a gas chamber where we have very different types of gases, and we have the proton that goes and collide with these gases at rest. So it's a fixed target mode that it's very important to see production of heavy flavors in different environments. So I'll start with CP violation and the differences in particle and antiparticles. First, not CP violation, but this oscillation between particle and antiparticle. Feynman said many years ago that the fact that particle can oscillate to antiparticle and vice versa is a phenomenon which quantum mechanics gives the most remarkable prediction. So in fact, if in the experiment I can produce a BS, which is a B bar and an S, is neutral, by a box diagram, it can convert itself to its own antiparticle. And this is predicted to occur at a rate that it's proportional to the difference of mass of the two B types, a heavy and a lighter type. And this oscillation should be very fast for BS. And LHCb has the capability of really see this really fast oscillation. This is 8 picoseconds. So in 8 picoseconds we can see, so we see in red is B bar and blue is B. So you create a B and it oscillates. So you see that there is this, when you have B0 bar, you have less B0 because one is turning into the other. So the sum of the two is the quantity that you have in fact, but one is oscillating to the other, and we can reconstruct both. And from this measurement, we can actually measure this frequency, which is the difference of mass of these two states. This is a very high frequency. This is the only experiment that was able to measure this. But we have all the types of measurement, and just want to show you these differences. So D also oscillates. This is also, we also measured, we are being measured with more precision. But the D has a much less frequency, and within its lifetime, it cannot go to a full oscillation. It goes just like a fourth, but we can see it. For B0, we can see one single oscillation, and as I said, for BS, we can see many within its lifetime. So this is very, very beautiful. But let's go to CP violation. Through oscillation, this was the benchmark. This is the measurement that gave the Nobel to Kobayashi Maskawa, the theoreticians that made the prediction, but this observation was made by Babar and Bell in 2001, and they won the Nobel 2 years later, 1 year later, which is the fact that B0 oscillates to B0 bar, but when B0 goes directly to a given final state, it does get no weak phase, but if it first oscillates and then decay to this same final state, it inherits a phase, which is the weak phase that the standard model predicts for CP violation. So this quantum path interfering with this quantum path gives CP asymmetry that is proportional to this angle. And when you see it's the amplitude is proportional. So by measuring the amplitude, we can measure this CP violation factor. And in fact, this is the most precise measurement that puts this constraint here to the CP violation in the standard model. So, but we call, this is kind of what we call indirect CP violation, because we see it through oscillation. But what we call direct CP violation, we can see by bare eyes that the counting of B minus decay to a given final state is different than the counting of the number of decays of B plus to a given final state. That means when we project, and this is because of the interference, always we need interference. When we project and we see the mass peak for B plus and B minus, you can see explicitly there are much more candidates for B plus decaying to this final state than B minus. So you see directly from reconstructing a mass plot, which is a very simple thing that we can do, that particle behaves differently as antiparticles. And what is interesting is that for different final state, you can have the opposite. That means more B minus than B plus. We do have CPT, right? CPT means that the lifetime of the B plus has to be exactly the same as the lifetime of the B minus. So somehow, although each process can have different rate, the sum of rates have to be the same. So if you do see more particle than antiparticle in a given process, there are other processes that have to have the opposite, because the sum has to be the same to obey CPT. And here we see like asymmetries of the order of 75%. I'm not going to go into details on this. I just want to show this plot because it's super beautiful. This is a particular decay where you do have a lot of one type and pretty much nothing in the other case. And this is the largest CP violation seen up to now. And this is the measure of one of the important parameters of the, and that LHCb was entered the game especially to measure this one. Our aim was to measure this with a precision of about 4 degrees, and we overpass. We have a precision of less than 3 degrees over the years. Okay, but we should have also CP violation in charm in very small quantities, but should be measured. We have a very large amount of charm decays, and in fact CP violation was measured in charm in 2019. I'm talking about 50 million decays that was needed, so we really need huge samples to see an effect which is of the order of 10 to the minus 3, which was measured. I'm not going into the details of this, but we know now that although this was a difference between two types of the decay, we know that one of the decays is leading to this number, which is the 0 to pi pi. So this is the only observation of CP violation in charm up to now. We are measuring a lot of different decays. We are not there yet, so I work a lot on this. We had the most sensitive study of CP violation, but did not find in D+, but any moment we hope that we're going to find. But what is really new, we are baryons, right? And up to now, although we only saw CP violation in mesons, in B mesons, in B sub S mesons, in kaon, and in charm, but any of them were baryon states like the proton. So this year we observed for the first time CP violation in one decay of the lambda B. A lambda B is a heavy proton where instead of UDU you have UDB. So it's more like a heavy neutron. You replace a D meson by a B meson. And again, to see CP violation, we have to have interference among processes with a weak phase and without a weak phase. And you can this is more modest, I know, but it's significant. It led to observation. We say that if we have more than 5 sigma, it's an observation because the chance of being a fluctuation is less than 10 to the minus 7. So this is just a 2% difference among them, but it's very significant. And this plot here is just for you to see that sometimes we may see big numbers like 20% of asymmetry, but with large error bars. This is not evidence. We cannot say anything about this. The one that led to the observation is this one that is close to 0, but the uncertainty is small enough to claim the observation. So far, this is the only baryon decay that we saw CP violation. We are studying many ones. There are a few ones that have prospects, but so far it's only this one. So let's move topics. Oh, this is just a sketch to show the history of CP violation from parity violation that was predicted by Li and Yang and observed by Madame Wu to observation of CP violation in 64, and then the observation in beauty and charm, and now in beauty baryons. So let's move to rare decays, which pretty much means search for new physics. So we can call rare, and then all the types of flavor changing neutral currents types that can only occur in second order diagrams in the standard model. These are rare, but then you start to have very, very rare, like lepton number violation, that the standard model puts very stringent limits. So let's see. One very important search that was the main goal for the start of the LHCb was the search for this process B and Bs into mu mu, because in the standard model it could only occur by these second order diagrams. But if you have supersymmetry, for instance, you can have these diagrams that that this could occur in much higher probability. So the predicted branching fraction, the standard model, is at the level of 10 to the minus 9. And in fact, we could observe this decay, not only at LHCb, but also CMS and Atlas. And the number that we find is super compatible with the standard model. And so this excellent agreement led many supersymmetry people very, very sad, because before LHC there is this big possibilities in the space parameters for observing certain models of supersymmetry, but with this measurement we could only live in this corner. So no new physics here, but there are some interesting anomalies that they're still surviving. So one of the things that we are performing is lepton universality tests. So we know from the Well, lepton universality is an accidental symmetry of the standard model, but we do know that electron muons and taus behave the same apart from their mass differences. So in fact, there are many processes that if you compare the rates, just changing electron to muon or tau to muon, they agree perfectly after correcting for kinematics. But I won't get into the detail, but this is one of the persisting measurements that are challenging the standard model prediction, which is, it's a three-level decay where you compare the decays of B to C, producing a pair of lepton and neutrino, and you compare different leptons. For instance, in this case, tau to muon. And this should be, the number should be like 0.3 or 0.2, depending on the, because I'm correcting for kinematics, phase space. And for many measurements, Babar, Bell, LHCb, we are like 3.8 tension with the standard model. This was higher. It got a little bit lower. This was over 4 sigma, but it's still one of the things that are bothering, or let's say having people happy that maybe new physics is around the corner. One of the models that could explain this is leptoquarks, but also like Z prime, etc. There are other anomalies in muon processes that you may have heard, the so-called B anomalies. For instance, this one, the B0 into K star mu mu. This is a very complicated analysis. This is a 4-body decay because the K star decays into K pi, and there are many observables, angular observables, that could be sensitive to new physics. So by measurement all of these observables and comparing to the standard model prediction, you could try to see differences. But the problem is that what we call standard model is something that has within, because of the K star that decays into K pi, a lot of hadronization, that means non-perturbative QCD that is playing there. So it's not easy to really have predictions. But this is a very new result. We have older plots on this. I'm showing this, the result for this year. Also putting the result for CMS, and persistently these two bins here are above the standard model predictions, where standard model means calculations based on non-perturbative models for, so these are the models. I don't know much about these models, but these are persistent tensions that are at the level 3 sigma and almost 3 sigma here. But we did see some anomalies, like the, have you heard about the RK and RK star? Anyway, it's one that disappeared. And there are many other anomalies comparing branching ratios. Mainly this one is also, we have an update that the branching ratios of B to phi, mu mu and phi EE is consistently lower than the standard model predictions. Although they do agree with each other. I mean, they don't have, there is no difference between muon and electron, but they are both below the expectations. So it's, we have to see this very careful. There is this, we can't see, but there is this compilation of anomalies for many measurements related to flavor physics, where we put here the central values and what expected from the standard model. So we see that there are a few, mainly these ones that I show, a few anomalies. But we have to be careful. It could be new physics indication or still some large hadronic uncertainties. The most clean observables are the LFU, the tests of leptonic universality, because you can cancel what is the hadronic part. And these are the tests that are good. There is no inconsistency. And the ones that we do see patterns are the ones that have hadronic uncertainties. Anyway, let's see what the future brings on this. Changing subject, we can go to exotic hadrons. So one of the things that the LHC was not prepared, the LHC was prepared to see one important particle, which was the Higgs, and then many other resonances that we can form is hadronic states. We can form many hadronic states, right? But then we start to observe what we call exotic QCD states, like tetraquarks and pentaquarks, and there are many of them already. So this is to have you the idea of there are now 79 new hadrons that were observed by the LHC. Most of them, 70 now, 70 at LHCb, and 24 of them are of exotic nature. That means tetraquarks or pentaquarks. So the idea is, let me put this all together. So we know that although we do, in principle, only see baryons and mesons, since the beginning of the quark model, Gell-Mann and Zweig already assumed that some states like pentaquarks or dibaryons or tetraquarks or glue balls could exist. They are not stable though, and it took a long time to observe them. And in fact, the first candidate, a strange in the sense that not expected candidate, appeared at the Bell experiment in 2003. It was not clear the interpretation. This is one of the most famous tetraquark and the most studied tetraquark to date. And then LHCb start, and also CMS also entered the game with particles with 2 muons in the final state. So some of these particles were discovered by LHCb, most of them, but not all. And this is the timeline of this discovery. I will start with the pentaquark because this is the most cited paper of LHCb. This one, you can check. When we saw this clear bump in this decays, should not have any resonance in the J-psi proton mass, and it appeared here. Then with more data, this was run 1, with more data, we could disentangle this part. So I'm going to show you a zoom of this part, and we could see, in fact, 3 states. So we have 3 pentaquarks here. What we do not know is whether these are really compact pentaquarks or like a molecular state, a tight bound state between, this is the 0 bar plus, what is that? The psi. I can't see in my screen here. Yeah, the sigma. Yeah, the sigma. And then we saw another pentaquark. So these are all the pentaquarks that we saw up to date, which is this one here. So the nature, it's itself not clear. Other searches are being conducted. We didn't see anything for now, but many, these are still low statistics. So there are many channels that we are still observing the channel today, and then to do what we call an amplitude analysis to search for resonances. So this is a very active field. For tetraquarks, there are many candidates. I'm going to show you just what we call open charm tetraquarks, because this is, we have a C, an S, and all 4 quarks are different. So this is clearly, manifestly exotic. You can see here, this is the peak. This is the phase space, what we call the Dalitz plot, and we can project and we see the peak, and we can analyze this. Oops. And in fact, we see 2 tetracarc candidates. And it also appears in other channels that I'm not going to show. Oh, in fact, this one I'm going to show. This is the same tetracarc, but here what's interesting is that it appears like with an interference. The tetracarc is this one, but interferes with other states and it gives these funny shapes. But the mass and the width are consistent with the other one. And then there are these what I call very charming tetracarcs, because we have 2 charms. This is also manifestly exotic, and it's a very clear peak. Also, we don't know, in all these cases, we don't know the nature. This is an intense debate. And this one that was seen for the first time by LHCb, but Atlas and CMS also observe it. There are interference with other possible tetracarcs like this, but these are CC, C-bar, C-bar states. And, well, I'm finishing my time, in fact, and there are many other topics which I won't cover. Some of them are in the backup and we can discuss, like some searches for new physics in ALPS and heavy neutron leptons, and this observation of a hypertriton, which is super beautiful, or the Z-mass, and about the future. So as I said, LHCb now is running, well, LHC is on run 3. It's going to end by mid-2026, when it then shut down for the preparation for the high Lumi. No, we still have run 4 and then preparation for the high Lumi. So LHCb, contrary to the other experiments, we have a major upgrade between run 2 and run 3 and 4. Exactly to be able to have more interactions, 5 that we have for each bunch crossing. For that, most of the electronics were completely rebuilt. We have a new vertex detector. We have replaced much of the REACH, which are the particle identification system, and I won't get into the details, but what was very crucial is that the trigger that we had a very bottlenecked, which is the hadron trigger, hardware trigger, that we now replaced by a full software trigger. I know you don't know anything about that. This is okay, but this is very important for us. A full software trigger means that online we can process every information through software. And we need to use GPUs as well as CPUs, and we can do the full reconstruction of the decay on real time, and calibration and everything. So this made it possible to only, because of the trigger, have 3 times more efficiency on and get to lower energies and PT, so it changed our lives. And this is the usual plot that we show. This is the integrated recorded luminosity. That means how many collisions we are getting. This is before the run 1 and 2 until 2018. But then this is the new era. So it's we're going faster. In fact, this week we reached 10 inverse femtobarns in 2024. So 25. So you can expect us to provide new results very soon. The problem is that the results are so many, and we have so much data that we are still actively working on run 2 and don't have time to work on run 3. But anyway, so in summary, LHCb has delivered hundreds, really hundreds. We have reached more than 800 papers so far, with many contributions. I didn't say anything on our heavy ion or fixed target because I don't have time. One of the interesting things, as I said, was the fact that we are really giving a huge contribution on QCD. So looking for new physics is very important, but understanding our current physics, it's super important, even to look for new physics. So we had major accomplishment on CP violation, also tests of the CKM ansatz altogether. There are a few intriguing anomalies in the B sector involving leptons, so this is interesting. We run at very different environments. I didn't say a word about this. And let's see what the future brings. Thank you.
Thank you very much, Carla, for this charming lecture. And at least I saw the penguin. That was the first time I saw it in this lecture. So please, questions. Any questions? Maybe I can start. My first question is about statistics. So I never understood this question of significance, but these anomalies that you said, it looks pretty significant in the sense that error bars are small. So why do you still expect that this to change, or
can you
so the anomalies that you showed, right? So they seem to have some of them.
So we are still limited by statistics in many of the measurements. So what that means, so usually we have systematic uncertainties are the ones that, let me come back here somewhere. So systematic uncertainties are those that we inherit from our machine, our techniques, our efficiencies, whatever, right? And this is, so for instance,
anomalies that look like they look pretty good, right? So they were small error bars.
Let me go there. I can't see. So in these error bars here, it's you can see the error bars are already they are small, but I mean this is already systematic plus statistic combined. We are dominated still by statistics. That means that there is room for improvement, so we just need to take more data. But I don't know, this was not your question, right?
Yeah, I guess, so what's the expectation? I mean, what will happen? You mentioned that in the past that some of the anomalies, they actually disappeared due to statistics. So what will happen, like in this case?
I don't know, because I mean, here, the problem is, two things can happen here. The problem here is more like here than here, I would say. It's a question of interpretation, which is where we bet more that there are still some problems in the hadronic part of this amplitude, because people call standard model, but it's not standard model per se, because it depends on a lot of models that relies on non-perturbative techniques, right? So for instance, this used to be even lower because people were not including like charm loops. And charm loops give some long distance contributions that were not being putted in, and this went up. So people are running out of ideas, the theoreticians, of how to understand that. But I think it's too soon to bet in any of them. So we want this to remain here, and the experimental error bar goes lower, then we can claim, oh, this is new physics. But many models of new physics also separate the generations, right? They see like the Z prime, whatever, they don't couple the same way from muons to taus to electrons. So when you do the ratios, you should see something. And that was the sad part, because we have the ratio, I didn't show here, but we have the ratio of this one compared to E plus, E minus in the final state. And this, we saw it a 3 sigma discrepancy in one of the analyses that we did. And then it faded away. So we don't see any difference from this one to electrons. It's exactly the same, the ratio. And we do see here, and the ratio cancels all the uncertainties that we have from the hadronic part. So this is why people are still happy that there is this discrepancy, so there is room to improvement, even in the theory part or the experimental part, to really understand what's going on here. The same for this one, right? I didn't show anything, but these are semi-leptonic final states. We don't see the neutrinos, and don't see the neutrinos in hadron machine is like a nightmare. This is better but you see Bell and Babar are not hadron machines, they are electron positrons, so the background, and they can reconstruct a neutrino. And Babar, Bell 2, I think this result here is already includes the Bell 2 measurement. And still, Bell 2 is here, you see? The error bar is still, the ellipse is still higher than Bell did, but it gets further away. And LHCb, it's this ellipse here, so in fact LHCb is consistent with the standard model, but it's a hadronic machine where we cannot see the neutrino. So maybe here something is happening. But again, you have taus in the final state. Taus decays into pions and many other, you can choose the final state with just muons, taus decay only to muons, but then you have more neutrinos, or if you choose the trial decays to pions, you have a mess. So maybe it's also still in the hadronic part, we don't know. And this is a 3 level, so this is not a rare decay, this is an abundant decay.
Questions?
Thank you. Is CP violation a necessary condition for meson oscillations?
No, these are 2 independent things.
Right.
So you can have oscillation, but without CP violation. So to have oscillation, all you need is this type of diagram here. So in fact, here in the BS that I showed before, this one has no CP violation here. So you just need this kind of process, and that's it. For CP violation, you have to have a process and another process that interferes with this one, which is this case here.
But we use CP violation to identify which particle or antiparticle is decaying, right?
Depends, not for direct CP violation. So the highest CP violations that we see are from direct CP violation. So from charged modes, B plus and B minus, and 3-level decays interfering with penguin diagrams that we have 80% of. This kind of asymmetry is that you have to have the oscillation, which is already kind of suppressed because it's a box diagram, and you have to have an interference between the oscillation and the direct decay. So this is what we call indirect CP violation. But and to observe it, you have to have a common final state. So yeah, so to answer your question, oscillation is one thing, CP violation in the other, and one of the CP violation mechanism that you can observe is through oscillation,
I see.
but not necessarily.
I see. Other question. So, do we expect CP violation in oscillation of neutrons?
Neutrons.
Yes.
The neutron particle.
The variant.
No.
Okay. And the LHCb machine is capable of distinguish neutron oscillation, or not?
You mean the neutron particle?
Yes.
DDU?
No, not neutrino, neutron. The variant.
No, you don't have oscillations there, because to have oscillation, it should be a meson, not a baryon. Because you have to have a quark and an anti-quark. That this anti-quark, let me show here. This anti-quark changes. It's a flavor changing effective current. This flavor change, B bar changed to D bar. So the neutron you have DDU, you cannot convert it to D bar, U bar, unless you have baryon number violation, which we don't.
Okay. So I am thinking on beyond standard model.
Beyond standard model, we can talk about anything.
It's anything, but...
yeah, but then you're talking about baryon number violation.
Okay. It's
so baryon number violation, you need to have more than, because I mean, you could, we had baryon number violation very, very, very early in the universe. But now to have baryon number violation, we do need beyond the standard model.
I see.
But we do not see any of the, at the level that we don't see any. We are doing kind of all types of searches also for baryon number violation. For instance, not a neutron, but for instance, we are doing many decays like proton to pion electron, or B to tau E, and so things like that you violate baryon number. So within the LHCb reach, what we do is this kind of searches. For instance, we have a search which is B0 decaying to tau muon or tau electron, which is both, it's baryon number violation and lepton number violation.
Okay, thank you very much.
And we are not seeing any of these very, very rare things so far. We are putting stringent limits, but yeah.
That's it. Okay, thank you.
Okay, thank you. So I think since we're a bit over time, so let's thank Carla again, and
thank you.
Further questions can be asked maybe later today.
To the shy ones that maybe want to ask anything.